Hello students, in this video we'll discuss the Dirac Delta Function. Consider a sequence of functions f(n) of t, which is defined as follows. It will be n if t is between 0 and 1 over n, and 0 if t is larger than n. So if we were to plot these functions, here's the t-axis, here's the fn of t-axis, we would see that the function f1 would be at a height 1 for 1 unit of time. The function f2 would be 2 for half a unit of time. And the function f3 would be 3 for a third of a unit of time. And then it would be 0 for all other times. We can see from these graphs that they form rectangular shapes whose height is always n and whose width is always 1 over n. So we can note that the integral from 0 to infinity, fn of t dt, is equal to 1. Now, we'd like to compute the Laplace transform of these functions. So, fn tilde of s will be the integral from 0 to infinity of fn of t e to the negative st dt. And now, the function fn is only non-zero between 0 and 1 over n. So this will be the integral from 0 to 1 over n of n e to the negative st dt. And so now we will see that this is exactly equal to n e to the negative st divided by negative s from 0 to 1 over n. And so now what we'll do is we'll plug in the limits. When we plug in the top limit, we will have a n e to the negative s over n over negative s. And then I'll have a minus minus, which will turn into a plus, plus n e to the negative 0 over s. Now this is just n over s, and this is negative n over s e to the negative s, so we can factor this by pull out an n over s from this expression. So this will be n over s. Then this will be 1 minus e to the negative s over n. And we'll write this in a little more suggestive fashion. We'll write this as 1 minus e to the negative s over n over s over n in the denominator. And what we can see from this is that that gives us a formula for the Laplace transform of fn as a function of n. And now we'd like to know what happens as n goes to infinity. Well, we can see from these graphs over here that as n goes to infinity, these functions fn become very, very large on a really, really small set. So, as n goes to infinity, fn of t will typically, while this expression doesn't make formal mathematical sense, will converge to a function which is infinity when t is equal to 0 and 0 when t is not equal to 0. Again, this does not make mathematical sense, but we can see what will happen. As n goes to infinity, the only value of t for which the function will be non-zero will be the value at t equals 0. Now, we can see what happens to this Laplace transform of fn as n goes to infinity. If we compute the limit as n approaches infinity of 1 minus e to the negative s over n over s over n. As n goes to infinity, this goes to 0 and this goes to 0. So we can see that this is the same as the limit as h approaches 0 of 1 minus e to the negative h over h, which is 0 over 0. So by L'Hopital's rule, this will be the limit as h goes to 0 of e to the negative h over 1, and it's equal to 1. So we have that fn tilde of s converges to 1 as n approaches infinity. And from this allows us to define the delta function. So delta of x is the limit as n approaches infinity of fn of x. And from this property over here, it's the case that we can define it equivalently as saying that delta, the Laplace transform of delta as a function of s, is equal to 1. So we see that unlike our other common delta functions, this delta, the Laplace transform of this function, is identically equal to 1 and does not tend to 0 as s tends to infinity. In fact, this delta function, this delta of x is called the Dirac Delta Function. And is not a classical function in the way we think of functions from calculus. And this Dirac Delta Function will have the following property. It will have the property that when you integrate from negative infinity to infinity of any function f of x against delta of x minus a dx, that this will be equal to f of a. Since delta is only non-zero when the expression inside delta is 0, that will say that x must be equal to a, and the property of delta that defines it will tell us that this integral over here will be equal to f of a. So these two properties of the delta function, namely that its Laplace transform is identically equal to 1, and that when you integrate it, shifted over by a units against any function over the entire line, you will just recover the value of the function at that point of shifting, are the two properties which define the Dirac Delta Function. Thank you very much.